Alright, welcome to CAB302 Week 8. This week we're looking at threads. Now, there is a fair bit to get to in this particular lecture, and I've promised to keep these under 2 hours, so I'll pretty much get right into it. So, this week what we're looking at doing is basically understanding threads, which are subprocesses that operate within a program and how they can be used in order to maintain responsiveness in a program when we're doing things that tend to lock up the CPU for a large amount of time. We'll be specifically looking at how we make use of threads in Java, and we'll be looking to understand and learn how to manage the problems that arise when we're actually using threads, particularly when they need to compete for shared resources. And, of course, we'll also be having a look at some of the difficult topics when it comes to threads: race conditions, deadlocking, and synchronization. So, first of all, what are programs, processes, and threads? Well, basically the idea is that we consider a program to be some executable that we aren't actually running at this point, or that we're not necessarily running. So a .exe file on a Windows system, for example, or a .class file, or a .jar file in the context of Java, would probably be considered a program. A process is what a program turns into when we execute it, and a process lives somewhere in memory. It has access to memory and file resources, as well as other potential resources such as network connections, and it runs on the CPU. Finally, we have threads, which are separate units of the parent process, and they share resources of that process. Now, what a thread is if you consider... Let's just find some code here. So, here we go. This is some code. We'll just work out. This thing has a main method somewhere. Yeah. So, when you consider how a program is executed, we sort of imagine an invisible cursor that starts at the entry point, the main method in the case of a Java program, and basically winds its way through that code almost line by line, at least from the perspective of the programmer. Code execution pretty much goes through the code in this kind of fashion, descending into methods and constructors and things like that when they are called. And that process of this invisible cursor going through your code and running it, that is essentially the thread of execution, or thread for short. And so, in a typical program that we just go and write, we go and create a main method and we call some normal methods inside that and so forth, that just has one thread of execution. A thread of execution that starts at the main method and continues on. If we end up in a situation where we have multiple invisible cursors winding their way through our code, executing it, that is multi-threading. That is when we have multiple threads of execution. Now, even this piece of code here already probably has... Well, okay, so this piece of code here, for example, starts at main, goes into this fill demo constructor, and then works its way through fill demo. So what happens with that is, this is all still happening in that main thread there. But then when we get to some code that makes use of swing, like this add action listener, for example, when that action listener is invoked, in other words, this action performed method is run, that will actually go onto another thread called the AWT event thread. And we can ask it to run stuff on that thread ourselves if we want, for example, but otherwise everything that is launched from AWT just runs on that particular thread. And so This is why operations that happen with inside action performed and other listeners, only one of these can actually happen at a time, and they basically happen in order of being executed. So all of these events pretty much go onto one thread and get executed in turn. So all of this code in fill, because it was launched from within the AWT thread, is still executing on the AWT thread. This do nothing method is also executed on the AWT thread, and so on. So that's an example. It's not really a typical case of a multi-thread application because this main thread is basically finishing up over here. It's just that because we have this other thread running, this AWT thread, our program continues to run, and it will continue to run until that window is closed by this, jframe.exit on close default close operation here, or if it's terminated in some other way. So threads are fairly simple conceptually once you get a hang of them, but it's the details that make them complex to use. And in terms of how they share resources of a parent process, every thread in the application has access to the same RAM. If you have some kind of global variable or static variable in here, all threads will be able to access that variable. As an example, they don't need to actually send that across as you would need for multiple processes. If you've got multiple processes, each one has access to a different area of memory, unless they've explicitly chosen to share some memory with each other. So why do we use threads? Well, there's two main reasons. The reason that we're mostly focused on in this unit is asynchronicity. And it's this concept that threads allow you to do multiple things at the same time. For example, we can, in the case of a GUI, we can, if we want to load a file and we know that that file is going to take a while to load, we could go and show a nice file loading animation while we're loading that file, because we can load that file on a separate thread and have it not interrupt the rest of our work. That's just one example. Or we could have, some thread that's in charge of playing sound or something like that. And it would, get instructions of what to play from the main thread, but it can just do that without interrupting any other parts of the program. So this is a very useful behavior. It allows us to write applications that are more responsive, applications that don't entirely freeze up just because part of them has to do some work. The other reason is parallelism, and this is more the performance-oriented reason. The idea is that we've got modern fancy computers with lots of cores, and if we want to create a single program that actually makes use of those cores in order to accomplish a particular task in less time, we need to multi-thread it, because if you just have a single thread of execution, that can only occupy one core. So if you want to make use of more cores, you need more threads of execution to be running. So with asynchronicity, in single-threaded programming, most statements block. That is, a particular statement has to finish doing what it's doing before you move on to the next one. And this kind of makes sense, if you've just got, int a equals 3, a times equals 2, you expect the int a equals 3 statement to complete before the a times equals 2 statement does. And that's because, and otherwise you can't really write a meaningful program there if the previous lines of code haven't been executed at a particular time. So those statements could be thought of as blocking. Now that doesn't necessarily matter because those are fairly quick statements to execute, but some statements, some code that we may write might take longer. It might take longer just because we're doing a particularly large job. We might have a large array that we need to go and process the contents of, and that will take some time. So that would be CPU blocking. Or we might have something like a file that needs to be read in. Reading a file from a hard disk is inherently slower than accessing data from memory. So there's automatically a little bit of overhead in there, plus the additional time of actually reading in that file. It may not be a heap, but especially if you're reading a large number of files, you'll certainly notice it. So that would be an I/O blocking task. And of course, anything that needs to talk to something else inherently has a bit of latency associated with that. So if you're making use of a network connection, you need to wait for the server, for your packets to actually reach the server on the other end, and for that server to get around to responding to you. So anything that you do that happens to require a network connection is itself blocking, and so you'll be stuck on that particular call to send data over to that network connection, over through that network connection. You'll be stuck on that particular call, for example, for potentially an undefined period of time. So if you want a nice responsive program, you'll probably want to be able to do other stuff in the background while that is happening, or you at least want the user interface to remain responsive. You sort of think with a web browser, if you open up your web browser and you go visit a web page, while that web page is loading, you can go and open up another tab and go visit something else. So you're able to make better use of your time because the application has multi-threaded those accesses, or has otherwise found some way of not being blocked by the data transfer. And so by running that an intensive task in an alternate thread, we can perform other work in the meantime, so that we're still able to do things, so that we can respond to user input, which is the most important if we're trying to make a responsive application, because we want to be able to, don't want the user to think that our application is frozen. We want our application to look like it's just as responsive as ever. It's just that this particular task is taking a while. So if we could show lots of feedback for that, the user experience of using our application will be a lot better. And parallelism. So I've talked about modern CPUs have many cores, but a single-threaded program can only take advantage of one at a time. So we need to do multi-threaded programming in order to write really CPU-intensive tasks. And this is the cornerstone of multi-core and multi-node processing. It's not a focus of this unit, although we do talk about some of the stuff that Java provides us to help us do this kind of programming. But it's covered more as sort of a theoretical angle in CAB301 and CAB302. And at the moment it's also covered in CAB303. So we'll be able to find lots of resources on this kind of parallel programming. But it's a kind that you want, that you'd probably be most interested in if you're looking to really make your CPU scream. So, programs, processes, and threads. In Java, when you launch a program, it has a main thread that's been created by the JVM. So that's the thread that you get that begins at the main method. And the programs that we've seen to date, with the exception of some of the GUI stuff, have been single-threaded. But programs can create objects that run in separate threads. Now, the JVM looks after threading for us. At some stage, those threads that... okay, so threads are typically taken care of by the operating system. The operating system is in charge of running your processes, and so if we want to have a process that runs on multiple CPU cores, the operating system needs to know about that because it's the only program with enough authority to go and schedule stuff on CPUs. But the JVM has its own threads that it takes care of so that it can do garbage collection and, So what this actually means is that the JVM, in addition to the threads, the main thread that you get and the threads that you can create yourself, the JVM also has a bunch of threads itself. It has a thread for garbage collection, so this is a task that pretty much runs in the background and triggers at certain times or in response to certain events and goes through your program just to see if there's any objects that need to be deleted. And then there's stuff like the AWT event thread, which we've had a look at already. That's another thread that's automatically created by the JVM. And there's a bunch of other ones as well. For example, there is a thread pool that's created for use with the new parallel streams stuff and the fork join pool code. So that's something that the JVM creates for you that you don't need to create. Any other threads you'll just create yourself, by creating an instance of the thread class. Threads can also have priorities that are relative to other threads, and this is used to decide which thread gets the CPU next. It's a little bit obscure how it works, so we don't really cover it very much in this unit. But basically, it's just used to work out, if two threads would otherwise run next, the one with the high priority is run first by the JVM. Okay, so this is the typical thread lifecycle, and this will be the case in any programming language, not just Java. But a new thread will start in a waiting state. This is basically a state machine diagram. When that thread starts, it will transition to the running state, at which point, something will happen. Either it will just keep on running, or it will exhaust its time slice, and therefore time out and move back to waiting. When a thread moves back to waiting, that means that another thread can come and start executing code. Alternatively, from the running state, it could enter a blocked state. This is where it's actually waiting for some sort of external event to happen before it unblocks. And we'll look at how we block and unblock threads with wait and notify near the end of the lecture. Or the thread can just complete, at which point it is terminated and the resources attached to it are cleaned up. Now, naturally, this is sort of the view of a single core system, which can only run one piece of code at a time. If we have a multi-core system, we can have this sort of thing happening in multiple areas, because we can, of course, have multiple threads running at the same time. You can still gain some performance improvement by multi-threading even on a single core system, because you can do stuff like making use of the CPU while the disk is busy on another thread. But most of the really great gains that we get are from taking full advantage of our multiple CPU cores. But despite how cool threads are, they are dangerous. And it's due to the fact that they introduce asynchronous behavior. And that means that if a thread communicates with or shares data structures, only one thread should be able to alter that data at a time. And that can lead to something called a race condition, which we will look at later. Java provides a high-level synchronization structure called a monitor, which is C-A-R Huawei. I'm not sure how to pronounce his name, but he's a famous computer scientist. And the idea is that we make use of a synchronized keyword to say that this particular method or this particular block of code is something that accesses shared data, and these are treated with this monitor structure. And all monitor means is that only one thread can enter at a time, and any other threads that get up to the monitor are put in a waiting queue until the thread that's currently in the monitor exits it. So the thread that's currently in your synchronized method, when that exits, the next thread that's waiting in the queue will be able to enter that method. All the threads that are waiting just do nothing until they are able to enter that. So we'll look at synchronized more later. But for now, we're going to look at the Java language constructs of how we actually make use of threads. So there's two main classes, one class and one interface, thread and runnable. And either way, we need to create a thread, but the way that we provide the code that is run on that thread differs depending on which of these two approaches we take. And so the idea by having both of these, by having Java lang thread and Java lang runnable, is because Java doesn't support inheriting from multiple classes. You can't extend from two classes. And so to make the class that contains the code that is to be run on the alternative thread, to make that class able to be more flexible and inherit from, say, something else, we have this Java lang runnable interface. And so a class can simply inherit from this interface, so implement this interface, and then implement the run method of that class, and then we can use that class, we can use an instance of that to create a thread and run that code on a different, for example, a different core. And this is just a quick example of some graphical code. And I'll switch over to that code now. But the basic idea is that we have this code that then goes and slowly fills up this window with these little black dots. Now, these little black dots don't take all that long to draw themselves, but because this code is trying to simulate some CPU-intensive code, what it's doing is each time it calls fill oval, what it's doing is it's calling this method that then pauses for 100 milliseconds of time. So we're drawing 10 of these black circles per second. And the issue with this approach is that while this code is actually doing that, this GUI is very unresponsive. We can't maximize, we can't minimize it, we can't close it. It's pretty much locked there. We can still kill the process, but because all of this code is running on one thread, that is the AWT event thread, nothing else can happen while this code is actually running. And so this is an example of a program that we would like to improve by introducing multiple threads in order to make it responsive so we can still move the window around and perhaps click other buttons and things like that. So let's stop that. And okay. So the idea is that the GUI is blocked until that fill method completes. And the idea is that if we put that fill method in a thread class, so fill is just this method that is looping through all of the x and y coordinates and drawing ovals. And so nothing else can happen until that method, which will take quite a while. Fill width. So we're talking 30 by 10, so 300 circles at 100 milliseconds each, 330,000 milliseconds, or 30 seconds, which is quite a long time for your GUI to be unoperational for. But if we put fill in a thread class, those circles can still be drawn, but without locking up the rest of our interface. And so this is a very straightforward background thread, and in this example, the approach used is to actually inherit this thread class. So we'll see how that works, but the basic idea is that we create a thread, and then, so let's just create a thread here, oopsie, and then we can either extend that thread in order to provide it with some code. So let's say we take that approach and override the run code. We can then go and write something, and this code, so thread is running. Good stuff. And we can also call, I was going to import a sleep function that I wrote earlier, so that we can just make this sleep for a little while, say 200 milliseconds. Oh, whoopsie. Go. And then we'll just say thread is completing. Okay. And now that, so this is just overriding the thread class and creating an instance of run. So now we can go and get that thread and start it. And just to show that we're also still running some code, we'll wait 100 milliseconds here and print out the main thread is still running. And then we can just run that. And what we will hopefully see, okay, so we start that particular thread, it starts executing, it prints out this message. Then the main thread over here gets up to, finishes its sleep, gets up to here, and prints out a message saying that, oh, this code is still running. And then this code over here runs. So we have two threads of execution, one of which is slowly getting through these 3 lines of code, and the other is continuing here. So it's continuing from there to execute those 2 lines of code. And when both of the lines of code have completed, the program terminates. A Java program terminates when all of the threads that are running in it have terminated as well. Or if you terminate it forcefully by using system.exit or something similar. So that's the Java lang thread extending approach to making use of a thread. The other approach is to create a runnable and pass that to it. So if instead of creating a new thread, we create a new runnable, what we can then do, we'll also create a new thread, and then instead of putting the code directly in there, we can go and pass the runnable to it. And then we can run that, and we can see that, as long as this works, the exact same thing happens. So these are just 2 different ways of applying the same concept. Before Java got anonymous functions and the like, the choice between these mattered a lot more because, you know, each time you create a new class, you had to go and create a new class over here. But now that we can just create an anonymous class wherever we like, there's not a lot of difference between the 2. I will say that this approach is a little bit nicer if we want to, say, run a couple of different threads with the same executable code, because then we only need to have one runnable, and we can just run those 2 and see. There you go, we've got 2 thread is running messages, a single main thread is still running message, and then 2 thread is completing messages. Okay, the 2 methods that we care most about are run and start. A common mistake people make when they're just using threads is to call the wrong one of these or to extend the wrong one of these. And if you do either of those, you will end up with code that is not actually running on a separate thread. And we'll sort of see why. Thread.start is the code that we use to actually get the thread to begin execution. That is code within thread itself. So that takes care of the job of spinning off that new thread and making sure that its code is, you know, this runnable. And so if we accidentally overrode the start method, we could write code in there, and that code would execute, but it would just be on the same thread. In the same way, if instead of calling the start method of a thread, we called the run method, which is perfectly legal. In fact, I don't actually know that it would do anything, because I think, that won't go and... I'm not sure if, IntelliJ actually tells me I should probably write start, which is quite nice. So thread.run there, if we ran that, that would potentially run code, but that code would still be on this same thread. We wouldn't accomplish multi-threaded code. And that can be a bit of a trap because, you know, you can see that your code is being executed, but it might not necessarily be obvious that it's not running on a separate thread. So we need to override the run method, and we need to call the start method in order to start running the thread. And then that will, in turn, somewhere within the guts of Java, that will end up eventually calling our run method and running this code, but running it on a separate thread. One of the nice things, though, is that threads actually all come with an ID. We can actually see that ID by doing thread ID is D, and then we just need to do thread dot current thread. So this is a static method that just returns the current thread that's being executed. That even works on the main thread. Get ID, and then we can use this to tell our different thread IDs, so our different threads apart. So we'll just say this is main thread, and this is still main thread, and we'll put some code in here. In fact, we'll change that to printf, add some new lines to this, because printf doesn't add them by itself. Thread %d is running. And we'll once again do thread current thread dot get ID, and maybe the same thing for this as well, is completing. So now we can run this example here, and we can see, okay, so our main thread is thread 1. The two new threads we created are actually threads 14 and 15. This is not unusual, this is not a surprise, and that is because you remember those threads that the JVM creates, those are also, those are actually already existent at that particular time. So the JVM's gone and created a bunch of threads, and now when we start creating threads, we start at 14 and 15. If we go back to this GUI code here, we recall that this code runs on the the AWT event handling thread. So let's go and do that same printf as before, but we'll just see what the thread ID is of some code that is supposed to be running on that AWT thread. So that's thread 18, so that's interesting. But you get so that's actually after our the threads that I just created there, and that must be because the AWT thread gets created once we start making use of AWT. Once AWT events start getting executed, then it goes and creates that AWT event handling thread. All right. So these are the methods. They're fairly straightforward, most of them. You can tell a thread to sleep for a certain period of time. There's this method called join, which is what we use when we want to wait for a particular thread to finish. So if we wanted to change this code here, I might just get rid of this debugging stuff. Alright, so now I'm going to go and join those two threads. So if I, these throw exceptions, I'll just add them to main's method signature so that we don't need to worry about them. But that exception will be raised if, for some reason, when we're unable to wait for this thread to finish, if it got interrupted for some reason. But otherwise, we can put in another print line and just say all threads are finished. And then we can run that to make sure that it really does wait until all threads are finished before that happens. Note that even if it takes a long time for that thread to finish, the main method will still end up waiting for it. So your program can essentially get locked up by waiting for a thread if, for example, that thread just never finishes, or if it has, or maybe if it's waiting for some event that only your thread can actually cause. So you just need to be careful about using that. And of course, is alive to see if the thread is still running. As we've talked about, you don't want to call the run method. You want to call the start method and override the run method. Okay, so this is an example of taking that fill demo from before and fixing it. So if we go to this code here, oopsie, I said I would increase the font size before. Okay, that should be a bit clearer. So if we go to this fill demo and have a look for where the code changes. So in the action performed method, instead of just calling the fill method, which is what happened before, it creates this object called packer and calls a start method on it. So if we look at what packer is, it extends thread, so it has that particular thing. So we'll open up the packer class, and what we can see here is that it extends thread and overrides the run method. And then from inside there, that run method's contents are the same as what fill was before. So it just goes and draws a bunch of circles, and it waits for 100 milliseconds between each one. And so what does that simple change end up doing? Well, if we go and start that, okay, so there are some slight downsides to the approach that's used to draw this stuff, in that, if you resize this window, it will end up blanking the contents of the stuff that's currently drawn. So that stuff then needs to be redrawn. But if we just leave it as is, maybe move it around a little, it's fine, and we can, we're not locked out of doing anything with this application. We can even click the button again if we want, and start another set of drawing happening in the background. So I think we'll see that if we, expand this. Yeah, now we're drawing these circles on 2 threads, 3 threads, and so forth. And so just by doing this, we've managed to make the program remain responsive, even if it behaves a little bit oddly now because we can resize it. We've managed to make it behave responsively even while it's doing something else. Now, I will say that the way that it's actually doing this is a little bit dangerous. We've said before that the reason we don't like to call our swing code on the main thread is because there's a possibility of this main thread code happening at the same time as the AWT event handling code. And if those are altering the same swing data structures, that can result in undefined behavior. So if we look at our Packer code here, for example, what this does is that it's actually making use of swing drawing code when it probably, in a thread that is not the AWT thread. So this stuff could potentially happen at the same time as AWT event code. Or, if we click that button a few times, we've just got multiple threads that are working on this same piece of code. The way to get around that is actually to make use of that swingutilities.invocelater function that we've looked at before, in terms of, where we stick our GUI creation code. But we can also make use of that here. So we can actually just throw in, I'm using a lambda here to make this a little cleaner. So what this will do is hopefully the same thing. It's currently glaring at me with a... Oh, I see. So I need to actually give it those x and y coordinates in final. So I'll give it final int draw x equals x, final int draw y equals y, and then pass those in, and it should be fine. Basically, due to the way lambdas and other anonymous functions in Java and other anonymous classes in Java work, you can only make use of external variables that were declared in the enclosing method if those variables are final. These variables are modified, so they don't qualify, but we can just store them temporarily in these final ints, and they should be fine. So now if we watch that experiment again, it probably won't do anything different. If it does do anything different, that means I've made a mistake. But we know now that no matter how many of these that we start up, that we have running at the same time, it will all be thread safe. It might be a little bit slower, and that is because swingutilities.invocelater basically puts this code at the end of the AWT event queue, and so this stuff will run on the AWT thread. The actual code to, do the waiting and all that is still running on this thread we created, but the code that is making changes to swing data structures is running on the AWT thread, and so it's all nice and thread safe. Okay, so once we're done with the thread, how do we get it to stop? Well, there are some methods, but the thing about those methods is that they are deprecated. So if we have a look at I'm just looking at the chat now. Move your mic a bit, there's a lot of scratching noises coming through. So my mic is actually on my headphones. I can I think I just need to move around less. I'll try to move around less and see if that makes things a bit better. Where can you get the demo code Lecture 8? Well, the demo code in Lecture 8 is just stuff that I'm writing now. The Lec 8 threads code, I think I should have uploaded that. If I didn't upload that, then I will upload it at the end of the lecture. Okay, so in Lecture 8, okay, yeah, so I forget where I was. Alright, yeah, stop, suspend, and resume are methods that are available in thread, but those methods are deprecated. So if we look in here, for example, if instead of waiting for these threads we decide we wanted to stop them immediately, we could use methods like stop or suspend, but that line through them means that they are deprecated methods. And that is because it's not recommended to forcefully stop threads. Now, just because they're deprecated doesn't mean they don't work. And we can run that now just to show you what that looks like. So, yeah, here we go. So main thread is still running. Then we get all threads are finished. And we got that here because neither of these threads got to this point. They were both forcefully terminated by our application. And that is because these thread stop methods were used, and those just forcefully terminate a thread. But that's not the recommended way of stopping a thread, and that is because there's a lot of downsides to not being able to clean up what that thread was doing, because it could be doing anything at this particular time. We don't know, and because we don't know what it's doing, we can't really do much to fix that up. We can't really do much to make sure that all of those variables get cleaned up, and that is especially true if one of those variables happens to have a lock on something. If it has a lock on a resource, and we'll look at synchronize later in terms of how we use these locks, but if it has a resource locked down and that thread gets forcefully terminated, other threads will not be able to make use of that resource. So the ideal way is to use is to either wait for threads to terminate themselves, or to ask threads to terminate and then make use of a guard pattern. That way we can make sure that the thread has completed its current work and can safely stop. So the old paradigm of using stop or using suspend and resume, they have similar problems. Suspend just means to pause a thread, and resume will start up again later. Those are still fairly dangerous though. But the idea there is that we can make sure is that rather than forcefully stopping a thread, we ask the thread to stop and then let it stop by itself. And the typical way of doing that is to take whatever action it's doing, and this is normally something that's performing in some kind of loop, and control that loop with some sort of flag that can be modified from other threads. And so, you would then have a method that sets that flag and call it something like end. You don't want to call it stop because if you're extending the thread class, that would be overriding the existing stop method, which you don't want to do. So this example here is some code that just spins off two threads, joins with one of them, and then asks the other one to end. So it just calls this end method. So this is the first thread. It just asks, it just does some user input. User input is sort of automatically blocking. When you are waiting for user input, nothing else can actually happen until the user goes and types something. So that is running on one thread, and that will terminate once the user ends up typing something. So that could be pretty much instantly, or it could take an indeterminate length of time. And then there's this other thread which is essentially just running in the background. And what it's doing is that it is just doing some calculations, sleeping for a very small amount of time each time, and then once it's finished, it will print out, the log of this number is this number. And so this makes use of this stop flag. And the idea is that we have this stop flag. There is something else we need to do in order to be using this variable properly that we'll look at in a bit. But otherwise, it's fairly straightforward. So stop flag starts out as false, and as this code executes, it stays false until this method is called. Now, nothing in this loop here will ever call that end method. However, some other code running in a different thread can call it. And then instead of calling stop on it and immediately terminating this thread and not being able to access the output, what it does is that it will then just set that flag, and then this loop will then terminate, and the thread will just end normally. So you still accomplish the same thing. The thread still ends, but the thread itself gets to determine what the best time to end is. So it is able to release any locks, it is able to close any files, anything like that that it is doing, and terminate on its own time. So that is the ideal way of actually asking a thread to stop. So that's the thread class. The runnable interface, we've already basically looked at this. It's just that instead of just extending thread, we implement runnable, override the run method, and then pass it into the constructor of thread. Just like that. And so this is just another example of some code that is implemented within this runnable. So hello runnable implements runnable. We've overridden the run method, overwritten it here as well. And then over here, instead of creating two classes that override thread, we're just creating two threads and passing them instances of our runnables. So that's all fairly straightforward. Okay, so a quick aside on service threads. This is a kind of special type of thread that is used specifically for things a little bit like this. Probably not exactly the same, but threads that are supposed to just run in the background until the rest of your program terminates are considered service threads or daemon threads. It's basically named after the idea of an operating system service that just runs in the background all the time. This is historically called a daemon. And so these service threads, they typically contain a never-ending loop, and in that loop they're usually responding to things. For example, they're responding to events that were raised by the main application. Things like that. They're quite useful in client-server programming. For example, the server might have a daemon thread listening on each port, and when the request comes, the daemon thread then responds, and so on. It's probably not a good idea to make this an actual Java daemon thread, because the main thread will frequently be the only thread running if you don't have any quests that are processing at a particular time. But we'll look into exactly what a daemon thread is within the context of Java in a moment. The JVM has a number of daemon threads that just run in the background. And that is stuff like your garbage collector. Anyway, to designate a daemon thread, you can use this method called setDaemon, and what that does is that it sets this particular flag in the thread. And what that means is that the daemon thread will automatically terminate when the program itself finishes. And that is, when all non-daemon threads are finished, the program will terminate. So how does that work in practice? Well, I just got a quick example I whipped up previously in here. We've got this code here that... Okay, so we've displayed a message, and this is a nodal message dialog, so it is blocking. But at the same time, this code here, this loop here, is just printing out this message and looping. And it will keep doing that. So once I click this, the main thread here will terminate. but our daemon thread is still going strong. So that's a problem, because now we just need to terminate it. If instead we set that daemon thread flag to true, what happens is that this thread will be running in the background while we have this message box open, but once we close that message box and the main thread terminates, the daemon thread will also terminate automatically. So it's sort of a shorthand way of doing this kind of process, where we ask the threads to terminate at the end, but we just let the JVM terminate it. Note that setDaemon and isDaemon are not deprecated methods, but they do have some of the same problems as forcefully terminating a thread, because the daemon thread won't really be able to clean up anything. Instead, it's sort of good practice to, when you're writing daemon threads, not have them do anything that requires cleaning up. If they're going to, for example, if they need to open up a database connection or something like that, it's probably best if they then spin off their own thread that is not a daemon thread in order to do that work. Just so, because then that thread won't be able to be forcefully terminated. Okay, so I've looked at the very basic method of using threads, which is when we schedule a particular task. What happens there is that, and so the time that we've done is when we do thread.start, and what that does is it just immediately begins running that thread. But what if we want to run some code at a later date? Well, there's this scheduled task API, timer task API, that can be used for scheduling a task to run at any particular time. So, if we want to do something that will happen in 10 minutes time, we could, for example, create a thread, have that thread sleep for 10 minutes, and then do the task. Or we could make use of the Java timer task and timer classes in order to achieve the same thing. And these basically let you schedule tasks that will automatically run on our JVM background thread. We still use a wrapper thread, but we don't need to make use of it. So, okay, so this is just an example of a scheduled task. I think there might be one in the Legate threads repository. Yeah, so this is the scheduled task, and this is the code that actually schedules those tasks. So what this code does is it creates a bunch of scheduled tasks, and it schedules them to run at particular time. So these all happen on this timer. So we only need to create one timer, and what we do is that particular timer, we then put a bunch of things to schedule on it. And that timer essentially has its own thread in order to do this. Now, note this isDaemon thing. What that means is that the timer's thread is a daemon thread. And that means that if, for example, this particular... So what this code here does after scheduling those tasks is it waits 7,000 milliseconds and then prints out end of conversation, and then the thread terminates. But if we made that something like 4,000 milliseconds and then ran it, what we would see there is that it would print some of these messages and then terminate. And that is because this timer thread is a daemon thread, and so it will terminate when the rest of our program terminates. If we made that false, then those threads would continue running. So it really depends on the exact task. If it makes sense for your scheduled tasks to execute, then even after the main thread has terminated, then you might just want to set that to false. Otherwise, if it doesn't make sense, then you'll set it to true. Note that because this has been set to isDaemon false, and nothing else has told this timer to stop, our program is still running. So if we do this kind of thing, we need to have some other way of terminating that process. Instead, it's best if we make the thread a daemon and have it just terminate naturally. Now, these scheduled tasks here, all they are is, they actually implement runnable at some point in this hierarchy. The timer task implements runnable, and that means that in order to provide it with code, we just need to implement this run method. But we also need to, we can also add some extra stuff in there if we want to customize it. Okay, so those are scheduled tasks. Next we get to thread safety, which is probably the trickiest part when dealing with threads, is to write thread safe code. There's some sort of general approaches to that. Threads that belong to only one thread alone are considered to be thread safe. So, which variables are variables that belong to one thread alone? Well, if we consider... Alright, I'll go back to Lex right here. Okay, so let's say I created a local variable here. This is a variable that's just inside this code, and a equals 5. That variable is thread safe, and that it is thread safe because every thread that actually executes this code will create its own local variable called a. So that will be thread safe. A variable that is, say for example, in fact I'll just put this into a, alright, so a local variable is automatically thread safe. If it's especially if it's a primitive like that, if it's something that's not a primitive, if it's an object, whether it's thread safe or not depends on, for example, where that object came from. So if this is a newly created object, then that's nice and safe. No other thread can interfere with this particular object. But if we got this object from somewhere else, if it's a reference to an already existing object, so I'd say object, my object equals new object, and we set object to my object, well, that is not thread safe. And that is because all threads, so both the main thread and this thread that are trying to access this object will access the same instance of that object. So that's not safe. And so if we have multiple threads that are manipulating this object, altering its contents or things like that, what that will do is it will create, make our code unsafe. We won't be able to depend on the contents of this particular variable. Naturally, anything that's sort of, say, a static variable of the class, those are also shared by everything, and so they are not inherently thread safe. However, instance and static variables are not inherently thread safe. If this is actually running within some class, like this fill demo here, any code that we have, any variables that are part of this fill demo class would not be thread safe because they can be accessed from the main thread, they can be accessed from the Java AWT thread, and in the case of the threaded fill demo, they can be accessed by any of the other threads that are created. So that's potentially quite dangerous. So, it all depends on which variables can actually be accessed by a particular thread. And in order to make things thread safe, where we need to make use of these variables that can be accessed in multiple places at once, we need to synchronize our code. Our class variables, these are also absolutely not thread safe. We can actually make a variable thread local in order to essentially make it thread safe. What thread local does, if you make a class variable thread local, that means that every single thread will get a different instance of that variable. Now this is no good if you legitimately need to share the contents of this variable, if you're using this variable for communication, but it does mean that your code making use of it doesn't need synchronization in order to be thread safe. And we need to write programs that are thread safe. If we write non-thread safe programs or programs with race conditions, these are when two threads essentially race to modify or access a variable. Threads with deadlocking, threads with live locking, programs with deadlocking or live locking. Deadlocking is where every thread is sort of waiting on another thread. Live locking is when there's some condition where the threads are still able to run, but they're still, looping until some condition is met, and so the program never finishes. And there's this concept of process starvation, which can occur if a thread needs to access resources, but other threads keep denying access to those resources. So, the main difficulty when it comes to multi-threaded programming is the concurrent access problem. And the main type of bug that you see in this is called a race condition, and that's where threads race to modify or get to a particular value. And this is because changes made to a variable by another thread are asynchronous changes, and we can't predict the state of variables that are affected by other threads, because our thread has no control over when another thread is running by default, and we don't know when that thread goes and does things. So in this sort of example here, Harry and Sally are watching a movie. Harry has 5 sweets. Sally eats a sweet without Harry knowing, and now Harry has 5 sweets but thinks he has 4. And this is a common problem in multi-threaded programming, where where a thread thinks that a particular variable has a certain value, but it actually has a different value, and that is because another thread has stuck in and changed something without you knowing about it. So let's say we go to our main thread here. So I'll just go and write private void. So let's say that this we have some code here where we have some private int value, and we code something that sounds perfectly reasonable, like if value is greater than 0, value minus minus. That seems straightforward enough, right? If the value is greater than 0, then we decrease it. So this code should never actually decrease a value to below 0. It should, at worst, go to 0. But there's no way for that to actually become negative, is there? But if we have func2 running on a different thread, so if this code also does the same thing, so let's say these two methods are running on different threads, and they basically get to the same location at the same time. Naturally, this value here is a class variable, or an instance variable, sorry, and if these are both running on the same instance of this main class, that value is going to be shared between those two threads. So let's say these two threads run at the same time, and value is, say, 1. So function starts running, it gets to here, it does this check, if value 0 is greater than 0. So that sounds good. But then all of a sudden the operating system decides, alright, this thread has been executing long enough, I'm going to send it over to this thread here, and this thread can start running. So this thread goes here and checks, if value is greater than 0, and then it actually gets to go into the code this time. It subtracts value by 1. So now value is set to 0. So it was previously 1. Now func2 has set it to 0, and we've gotten to the end of func2's code. And so as a result of that, the operating system decides, alright, this code can continue running. So it's already passed this check here. It just decreases value by 1. So now value is negative, even though we had this nice little if condition in there to make sure that it isn't. And that sort of problem, and problems like it, occur a lot in multi-threaded programming. because you want to make use of the same variables from different threads, but doing so is dangerous. One thing that can be done is to qualify shared variables with the volatile keyword. If you've used volatile in C or C++, in Java it's very different. So forget what you knew about volatile from that. Volatile in Java just means that reads and writes involving this variable will be atomic. That is, one thread won't see a variable that's only been half written by another thread. And in addition, threads will also know immediately if a value has changed. So if we go back to this example here, this is the kind of thing that is not actually protected by volatile. But if we made it a lot simpler, let's say we made it look like this. So value minus minus and value minus minus. So that looks simple enough, and we'll just set it to 2. So let's say we run these two threads at the same time. You would think that after running these two threads, the value of, value would be set to 0, because we've subtracted it twice. But it doesn't quite work out that way. One of the things is that one of the problems is that value takes part over at least 2 different operations. Typically 3 operations, but I'm not sure the exact details when it comes to Java's bytecode. But normally a CPU can't perform additions, subtractions, anything like that directly on a value in memory. So we need to load that value into a register. So we'll just call this register reg. We need to load that value into a register, which is one of those high-speed high-speed memory units that sits on your CPU. The CPU does have operations for doing things like decrementing a register though, so we can just do reg minus minus. And then value equals reg. That's essentially what's going on there. We're loading this register with this value, and then subtracting 1 from that register, and then storing that value back into the value memory. So this is what's really happening here. And the problem is that programs can be preempted somewhere in the middle of one of these instructions, at which point you could end up with, this program sort of starting here, where we've stored a reg here, and then getting preempted, so func2 runs. Func2 might complete entirely, so value is now set to 1, and then the original function resumes, and it does its calculation. So reg is still 2, it gets subtracted by 1, so reg is now 1, value equals 1, and so value is now 1, even though we've subtracted it twice, just as a result of this operation. The other thing that gets in the way is that our changes to a value aren't necessarily going to be noticed immediately, because a thread, so your programs essentially get optimized for as if they were running on a single CPU core. This optimization can happen at the compiler level and can happen at all other stages in your program. And the idea is that the compiler or the CPU will go and decide, alright, if you're doing a bunch of things that sort of rely on these same values, let's say you're doing a value minus equals 1 and then value times equals 2, why do we need to go and store this in a register? So load this value into a register, perform this operation, and then store it back, and then load it back from that register. We'll just keep all these values in here because the compiler and the CPU will assume that because we can see this value here at this particular time, and our code isn't doing any other things, that it just can't change in the middle of our code. But if we're dealing with multiple threads, that assumption is very misguided. Volatile helps deal with that assumption. When we say private volatile int value, what that means is that this just tells the compiler that it shouldn't make any assumptions, that it needs to basically recheck the memory associated with the value every time it manipulates this. So if it goes and stores it, it will get fresh memory out each time. And so, using volatile makes your code slower, at least for accesses to that particular variable, but it also allows you to gain some semblance of thread safety for certain types of operations. And that's, not necessarily going to help us for this particular case, but it does help in a lot of cases. So with volatile, what that means is that reads and writes involving this variable will be atomic, and access to the variable will be surrounded by memory barriers, ensuring that the value appears the same in every thread. So it will re-retrieve the value of value each time, rather than assuming nothing else can change it in the background while this is working. So in the case of our previous example, where we want to add a flag that continues until we call this method to tell it to stop, technically, and this often isn't the case, thankfully, that sort of example code from before, which I will try to find wherever that was. Oh dear, it might have been quite a while ago, but we'll just have a look at this particular example here. So the example code from before, where we called a method to set this value, that example code did not use volatile, and so this run code here could potentially be within its rights to just assume please stop, can't change, because there's no code in here that changes it. So why does this code need to check the value each time? Because it doesn't do anything. But because we've labeled it as volatile, it does need to go and check each time. So setting this as volatile is the safe way of introducing this kind of programming construct. Another race condition example, so this is a lot more similar to the one we had before, where we have, for example, one thread incrementing a bank account value by 5,000 and another thread subtracting 5,000. And the issue is the same as with our value minus minus code here, in that because this stuff doesn't happen all in one operation, we could potentially interrupt it in the middle. And volatile doesn't help because even though it doesn't assume that the value can't change elsewhere, if it still changes in the middle of applying that operation, you're out of luck. And so what can happen in this case, if we have these two threads running, is that you could pretty much get any result. You could get a value of 0 at the end of it, if the bank account was originally 5,000, and that is because, this result overwrote this result. You could get a value of 5,000 at the end of it if both of them ran properly, or negative 5,000 if... No, you couldn't get negative 5,000. You could get 10,000 though. There we go. And so a better approach for that is something called an atomic variable. And these are found in Java util concurrent atomic. And so these give us some kind of special values that we can basically apply instead of making use of volatile. So rather than making use of int here, we might use atomic integer. We better import that. Equals new atomic integer, and we'll give it a starting value. And so rather than using value minus minus, we will use value dot, we'll use add and get. We're not actually interested in the result, but this is closest to what the change we want to make. And these values will happen in one go, so rather than, and can't be interrupted in the middle. So what happens is that if these two threads run at the same time, initial value will definitely, the value of value will definitely be reduced to 0 no matter what happens. And so that is a fairly safe way of doing this kind of approach. There was a question, shouldn't the slide be the other way around? Has 4, thinks 5. So we're talking about... Yes, you're right. Yep, absolutely right. Harry has 4 sweets, but he thinks he has 5. Thanks for spotting that. Okay. And so, yeah, if we have our bank account operations applying add and get simultaneously, we will always get, the value of bank account will be the same as it was before, because both of these operations will be completely carried out, even if the threads run at exactly the same time. So atomics are one sort of safer way of dealing with this. But here's another potential type of race condition, and it's most similar to the one we had before. So this one involves a stack, and that's probably because if you call pop on a stack that is empty, you will get an exception. So that's sort of your program blowing up. You'll definitely notice that. But it's similar to what the example we had before, where, we had that particular value, and we wanted to, we'll make that 1. To if value is greater than 0, value minus minus, and have that running in both threads. And so this isn't helped with atomics at all. There might be some methods that sort of get you some of the way when you're just dealing with integers. So you might be able to check. So you can use get and add to make sure that the original value was correct and was what you thought it was. But if you're working with a stack, like in this example here, there's no atomic option available for you, and volatile doesn't work for you either. In a case like this, where you have these two methods running at the same time, and the possibility is that thread 2 can run in between if stack is not empty and stack.pop, then you really need to make use of a proper lock. And here we can make use of the Java synchronized keyword. So, concluding this, before we talk about synchronized, I'm just going to present a sort of classic problem from multi-threaded, I guess, programming, and that's called the dining philosophers. And the idea is that you've got 5 philosophers that sit at a table. Philosophers can either be eating, which they need to do by grabbing both forks. I kind of prefer the version where the plate is a plate of rice and they have chopsticks, because that makes a lot more sense than needing 2 forks to eat a plate of spaghetti. But in the stand-up approach, a philosopher needs 2 forks in order to start eating spaghetti. And so what happens is that the 5 philosophers sit at that table. They have 2 states. One is thinking and the other is eating. But there's only 5 forks. And to eat, a philosopher must pick up forks left and right. And they always eat in that particular order. So this philosopher will pick up his left fork, and then his right fork, and then start eating. And once he's done eating, he'll put down those forks and resume thinking. And so, these are the philosophers are essentially threads, and the forks are shared resources. And so, yeah, we've got 5 forks, 5 philosophers. That's the way it works out. And so, this introduces the problem of deadlock, because if this philosopher picks up his left fork, and this philosopher picks up his left fork, and this philosopher, and so on, then every philosopher will have picked up 1 fork and be waiting on the other. But the philosopher that they're waiting on isn't currently eating it. That philosopher is waiting to pick up the other fork. And so the philosophers all end up starving. And that's the basic illustration of deadlock. It's where you have a bunch of processes that can end up waiting for each other to complete, but because they're waiting on something that another process does, they will wait forever. Then there's live lock, which is where a thread acts in response to another thread and makes no progress but isn't blocked, so the thread is still executing code, but but isn't actually making progress, isn't getting closer to finishing the task. But not, so thread states can do change, but we don't make any progress with any of them. And it's sort of viewed as being the corridor dance to the excessively polite. When you meet someone in a corridor walking in the opposite direction to you, and you both sort of move back and forth trying to let the other pass, that's essentially a sort of illustration of a live lock. There's also the concept of starvation, which is where some threads are allowed to be especially greedy in terms of making use of resources, and certain other threads never get the resources they need in order to be able to complete, and so those threads just continue running forever. So those are sort of some of the classic problems with dealing with locks. But how do we make use of locks in the first place so that we can run into these problems? We need to do synchronization. And the idea with synchronization is simply that we're trying to get threads to run in a particular order. So these are cases where, like our example before, where we want these particular threads, what we want is for one of these threads to do its entire execution first, and then for the other thread to run. And we don't really care which happens first, we just care that they don't do it at the same time. That is an example of synchronization. And so, in a share trading example, you might place an order to sell stock ABC, and then place a buy order for stock XYZ, and where your buy order depends on getting the money from that sell order. And so the sell must complete before you can do the buy, or you'll have insufficient funds. So you basically need to synchronize those two operations so that this happens and completes before this begins. And the solution there is to ensure that only one process occurs at a time, and this transaction must be synchronized across different threads. And so in summary, synchronization is just about only allowing one thread access to something at a time. And so this is just a piece of code. All it does is it displays a message one character at a time. And so what happens with that is, these two messages end up being displayed, but the characters are all jumbled together, so you get a huge mess. The way to resolve this kind of problem, and several of the other problems we have, is, or one way of doing it, is through the synchronized keyword in Java. There's two different versions of it. One is the method lock, which is where you just apply synchronize to a method. And that is pretty straightforward. You could say private synchronized, whoopsie, I went and replaced the void there. Synchronized void function. This wouldn't work, but let's just imagine that this function here, because this other function is identical, let's just imagine that it's just this one function that's being called from two threads. By putting this synchronized label in there, we're ensuring that only one of those functions can actually execute at the same time. The other kind is the object lock, and that is where you designate an object to be kind of the MacGuffin. It's the MacGuffin of this particular operation, for example, this particular lock or this particular set of locks. And what that means is that only one thread can actually hold the MacGuffin at a time, and the thread that's holding it gets to execute the code that's within this sort of synchronized region. And so by making use of that, we end up locking out other code from running. So if this is just a single method version and we're running this method from two different threads, because we've got two threads here, let's say that we just run that func method, which we probably can't do because it's not static. There we go. So let's say we were running that in those two different places. What would happen is that only one of those pieces of code can actually run this method at the same time. The entire method is locked, and as long as any thread is currently executing this code here, no other thread can even enter this method. What happens if another thread tries to call it is that that other thread will just be waiting outside. The object lock version is a lot more versatile, and also allows us to handle this case where we have, two different methods. So here we have func and func2. And so we can't really make those synchronized. I mean, we can make those synchronized, but it doesn't do anything for us because they're synchronized separately. This code could run and this code could run at the same time, and the compiler will just, and Java will just think, oh, that's completely okay because they're separate synchronized methods. As long as they're not both running at the same time, it's fine. So in a case like this where we have two different methods that are manipulating the same shared value, we would need to apply object level synchronization. This kind. And in order to do that, we need an object. So the easiest way, any object will work on this, including just an object. So we'll call this object lock, and we'll instantiate it. One thing that is it's not a requirement of locks, but it is highly recommended, is to make them final. By making them final, you know that the value of this lock will not be replaced by some other object that may not represent the same lock at some point. By making it final, you know that all of these locks that make use of this object are safe from that happening. So then we just use the synchronized keyword and we pass in the lock. And what happens here is that if a thread gets up to any of these, it will check if this lock has been acquired or not. If the lock has not been acquired, then it will be able to enter this code and execute it. And then once it gets to the end of that block here, it will release that lock. So that lock will no longer be acquired, and it will continue on. On the other hand, if the code gets up to a lock, gets up to a synchronized block, and finds that the lock in question has been acquired by some other code, then what will happen is that it will wait at the beginning of this block for that lock to be released by something else. It will essentially wait in a queue of everything else that's waiting on that particular lock until that code finishes. So I've got another example here. Test synchro, yes, this is it. So this particular, and I'll blow the font up a bit. Okay, so this particular example here, what it does is that it just creates two threads, and what these threads are is, well, you've got one thread that has a loop of 1,000 and it deposits funds. So we have a bank account, and this is just a very simple class. It's a simple class that controls this variable called funds, and you can deposit funds, you can withdraw funds, and you can get funds out. And in this test synchro code here, we've got one thread which for a loop of 1,000 just deposits $1 into that account and then sleeps for a millisecond. This other thread here, for a loop of 1,000, it withdraws $1 from that account and then sleeps for a millisecond. And then what happens is that it prints out the amount of funds at the end. And we can see what should happen. We've got $1 million. We're depositing $1,000 and then we're withdrawing $1,000. We should still have $1 million at the end of it, right? What happens if we actually run that code? Nothing. Why did nothing happen? Is it because this is too small? Yes, it is. Oh, we've got $1,004. That's weird. Let's run it again. oh, now we've got $999,999. And that is the problem. So you can see these don't happen a huge number of times. We're only getting single-digit errors, and that's of doing 1,000 operations at pretty much the same time. So these two threads are starting at the same time. And there's only a few cases in which they actually collided. And that is one of the things that is so hard about debugging race conditions, is that, you know, modern CPUs are so fast that it's pretty unlikely for this stuff to actually be a problem. It'll need to happen a lot. And the problem is that in modern, in software development, where you're writing code that's going to be used by lots of people, or writing code that's going to be shipped or run on servers many times, you will see those events that only happen 1 in a million times or whatever. And so even though it's unlikely for a given race condition to happen like this, it still does happen. And so this is some code that we need to synchronize in some way. And as you can see from just the way this works, volatile probably won't do it. We can try volatile. So we could say private volatile int funds and see if that works. Let's run that. Nope, it has not worked. It slowed down a bit. You definitely saw that took longer to execute, but it's still just as broken. So if we go back here, we'll just get rid of that. Instead, what we need to do is make use of something. So clearly our synchronized keyword, did I put that in the wrong place? Okay. Our synchronized keywords aren't going to quite work here either, because we have two methods that are actually handling this stuff. So once again, it slowed down our code. I know, they have actually worked. That's pretty nice. I wonder if we just got lucky. Let's run it once more. If it returns $1 million again, I'll assume that, okay, this has actually worked in this particular case, so that's quite nice. So we don't necessarily need to make use of the lock, but locks are more flexible anyway, so it's good to sort of get used to using them. And the way we make use of that is simply that we have this lock, we've made it final. All we need to do is synchronize on that lock, and of course when we do that, see, everything is nice and good. It's a bit slower. Now, one of the things about synchronization is that it inherently slows down your program, because synchronization is the act of, making a thread wait for another thread. It'll never make your code faster. And so it's just something that, sometimes it needs to be watched. But that's the basic idea there. By synchronizing that bank account, for example, we have things that are running, that are able to run and perform all of these operations in different threads at the same time without having any problems. Okay. So that's the synchronized lock. Synchronization sets a lock on the method or object. Don't overuse it. You only want to lock the code requiring exclusive access to the object or class. If you lock other code, then it will need to run that other code, but it will only be able to run that at a piece in one thread at a time, essentially. So the best way is to just synchronize the area that manipulates a particular data structure. This is something that can be quite tricky to get right, especially because if you synchronize, the wrong areas, or you have a bad order in which classes actually depend on other classes, you can get things like deadlocks. But otherwise, synchronization is a pretty good way of writing code and making sure that it is thread safe. The JVM and the operating system create the lock and manage its allocation. So the fact that it's in an object like this is pretty much just labeling. You need to actually have the lock assigned to something so that you know where it is. But you can make that anything if you're using a different class for something else, or let's say that the data structure in contention is actually that particular value. Well, is actually an object. You could make it the lock. You can lock any object. It's just that in this case we've created an object just for the purpose of our locking. The request is automatic and satisfied if the lock is available, otherwise the code waits for it. And when a synchronized method terminates, that particular lock is released. So once you get to the end of that synchronized block or the end of a synchronized method, the lock will automatically be released after being acquired at the start of the synchronized block. So there are different levels of synchronization. You might have no synchronization, you might only have your class method synchronized, or you might have both class and instance methods synchronized. And these depend on the level of the kind of data that you actually manipulate or have shared between different threads. So you just need to work out what variables am I using, where can these variables be seen from, which threads can see them, which threads access them, and then work out how much synchronization you need. Okay, the last topic of this particular lecture is about thread communication, and it's a little bit of a doozy, but basically what we want to talk about here is what you do in cases where you want to where you have threads that are waiting on other threads, but you want some kind of communication between them for some reason. And that's normally, the way that works is to, for example, allow a thread to get into a particular critical region. So why do you want to do that? Well, it's purely a performance thing. The basic synchronized lock approach is fairly brute force as far as synchronization goes. It definitely works. Only one piece of code can get in a region that's locked by a particular lock at a time. But it may be a bit overkill for some areas, and there might be better ways of actually doing things. So I have this class here, which I've called test notify. And in this code, I've created an instance of something that we call a producer-consumer pattern. And this is a pretty common pattern in multi-threaded programming. The idea is to have threads that perform some kind of task, typically on a loop, that produces data for some other thread to make use of. And a lot of programs can actually be decomposed into this producer-consumer model. The basic idea is that, we've got these two threads here. One produces widgets, and I've just got a 1 second sleep in there to simulate the producing of a widget. And the other one consumes widgets. And so we could imagine this being, let's say something like, let's say we have, for example, a program that, a thread that sits in the background and downloads, say, videos from some video sharing site. And so it just crawls that site, it finds videos, and then it just starts downloading them, and it stores them somewhere. And we then have another thread, and that goes and takes those videos that were created by that first thread, and goes and starts converting them over into some other format. And that takes quite a while. It's a very CPU-intensive task, but we can do those at the same time because one is mostly waiting on network traffic and the other is mostly waiting to use CPU. So by doing those at the same time, we can save quite a bit of time doing that. So while this thing is sort of converting an old video, this thread over here is downloading another new video to work with. And that's fair enough, but how exactly do we lock this? We pretty clearly have a synchronized data structure here, and that's fair enough. So we've got this, I've got this widgets, and it's a double-ended queue, and we've just got objects representing that. And the idea is that in order to produce a widget, producing a widget will just add something to the queue, and consuming a widget will remove that thing from the queue. So if we wanted to synchronize that, obviously we could just create a lock, so something like private static final object lock, and then we can just synchronize based on that. So synchronized lock. We don't want to do the actual consuming CPU intensive code in there. The idea is that we only want the manipulations of that queue to be locked. So let's go and run that and just see what that does. Oh, we've got an exception. That's not good. Why did we get an exception? Well, that's because in consume widget, it went and wrote and attempted to remove something before the first thing was created. So that won't do. We need to actually make sure that we consume something first. So how do we deal with this? We could do, if widgets dot size is great. Actually, I think there's like is empty. If widgets is empty, then is not empty, then we can remove this. But otherwise, what do we do? If we don't do that, then we haven't obtained a widget that we can actually consume and do this sort of simulated high CPU code with. So we need to do something else at that point. We might need to, should we wait for a certain amount of time before we go and consume the next widget? How long should we wait? Do we want to wait, say, a second? 10 seconds? 1,000 seconds? I don't know. We know we need to wait, but we don't know how long. And every time we sort of go and check, we need to lock this whole thing down. So let's say we made object is null instead, and we just, put this in a big loop. So while object is null, it will just keep checking this until it can obtain an object. So what will that do? Well, hopefully that will work. Alright, so each time a widget is being produced, it's now being consumed pretty much immediately. So that's fine. But this approach is not really all that great because it is continuously performing this loop. It is continuously going back here and locking down this lock each time. So this is wasting CPU. You could imagine this is a fairly large-scale task, so it probably doesn't matter. Each widget takes a second to produce or consume. But what if we've got a huge number of these? Then the overhead starts to matter. And this is where we introduce the concept of wait and notify. These are methods that we use on our lock object. And the basic idea is that we use wait in order to basically wait for some condition to change. When that condition changes, and we're waiting for a condition that can only be changed by another thread. So in the case of the consumer here, if we waited, we would be waiting for the producer to produce a widget. And we do that by using these methods. So in this case here, we get our object, and if the object, if there is a widget on that queue, things are fine. If there isn't a widget, we need to do something else. And we don't want to just keep on spinning over here, relocking this structure and checking over and over again. And we don't want to wait for an excessively long amount of time either, because then we're potentially wasting time when we could be spent consuming widgets. So instead, what we want to do is we want to make this thread basically go to sleep and then wake up when it's time to produce that widget again. So often what we would do is we would actually change this loop around a little. So we would do something like while widgets is empty. And so we know that at the end of this loop, we will be able to get a widget and then consume it. But what do we do inside here? Well, we need to wait. And this will throw an exception, so we'll just try and catch that for now. We might need to do something with that, but I think we can pretty safely just ignore that one, and our code will be fine. So I'm going to, by convention, just write ignored. Okay, so this will get to this, and if when consume widget runs, it checks widgets and finds that this code is empty, it will wait. And then after it gets out of waiting, it will check again, and if it has to, it will wait again, and it will just keep waiting until remove first. If we ran this code as is, it would just wait forever. And more importantly, it would wait, but without, and so the producer will just keep on producing widgets. So why is the producer able to produce widgets when we have this synchronized block here? That is because wait actually is designed to release this lock. Because while your thread is waiting, it's not doing whatever kind of operations it was doing before. All it needs to do, and so we know because it's waiting that it can't be accessing, say, shared variables or anything like that. So it is safe to release this particular lock. What happens is that when this thread stops waiting, it will reacquire this lock. So we don't need to do anything. We don't need to re-lock it or anything like that. We don't need to release a lock, check a variable, and then lock it again. This is an ideal way of doing it. And so what we would do here is that in our produce widget code, when we create a new widget, we will notify anything that is waiting for a widget. That could be nothing. And so now what happens is that the producer produces widgets and the consumer consumes them. And this will even work if, for example, let's say we made the consumer, let's say we made the producer a bit faster than the consumer. And so, yeah, things will still be fine. We'll be producing more widgets than we can actually consume, but everything is fine because we can hold an unlimited number of those. If we wanted to limit this, on the other hand, we could say that, for example, you can only have up to 10 widgets waiting in the queue at a time, and then when we go to produce them, we could check that value and potentially have produce widget wait, and then consume widget notify when it goes and consumes a widget, because then there's space for the producer to produce another one. And that's the basic idea. It's so that you can manage this kind of structure where, rather than locking things out, you in the middle of locking things out, you can actually go and allow another thread to go and do its work because it's doing something that you're waiting for. So you don't need to have a loop where you continually check. This will spend a lot less CPU on that kind of thing. There's a couple of different wait methods. You can specify an amount of time, even down to nanoseconds, and what happens is that if that time expires, if say 1,000 milliseconds expires without any this notify happening, then this thread will reacquire this lock and then continue its code. So you might do that if you want to do something else every now and then. Maybe you want to, because let's say that this is one of those background threads that I talked about before, and you're looking for a particular flag to be set to tell you to stop. You might just check that flag every now and then, or something like that. But if you just don't pass in anything, it will just wait until a notification comes in. There's also two versions of notify. One is notify and the other is notify all. And this wouldn't matter in this particular case because we only have one producer thread and one consumer thread. But if we had a bunch of each kind of thread, which we might want to do, you often see the producer-consumer model used in cases where you're trying to make as much use of the CPU as possible. And so you may have a bunch of producer threads and a bunch of consumer threads, and you might adjust the numbers so that the consuming happens at about the same rate as the producing. In that case, what happens when you call notify is that only one of the threads that is currently locked and waiting will be notified, will be woken up. If you call notify all, then all of the threads that were waiting will be woken up. So notify all can end up wasting a little bit more CPU because every thread will then go and check if particular values, if there's say another widget to consume. But it can also be safer in terms of avoiding deadlock than just a plain notify. So yeah, the idea is that you normally want to make use of some kind of checking loop like this because there's a few reasons that notify could be called. You might have your code that sets that particular flag might also send a notification just to wake up that particular thread. Or, if you've got multiple producers, multiple consumers, multiple queues, that kind of thing could happen. So we make use of wait so that we don't have to have this lock spinning constantly. We just wait until a thread has produced something because then we know we will be able to consume it. Notify, you can't specify which thread gets woken up if you have multiple threads that are waiting. The JVM makes that decision, and that's useful when all threads are waiting on the same condition because only one of them gets woken up and consumes a bit of CPU. But notify all, on the other hand, wakes up every thread, which can be useful if threads are waiting on different conditions, but only one unblocked thread can obtain that particular lock again, because once the thread is sort of woken up, it automatically obtains that lock. Okay, so now there's just a couple of quick cleanup topics. One is threads in Swing, and this is something that we've talked about pretty extensively. The idea is that your event handling code in your Swing GUI application runs on the AWT event thread. And so what you want to do is put all your GUI creation code in a Swing utilities.invoke later. And this is just a generic method that will run stuff on the AWT thread. And this is very useful because if you have another thread, like in our previous example, if you have another thread that is wanting to make changes to AWT, it can also call this stuff to make those changes rather than making them itself. And that way everything is nice and safe and thread safe because AWT does not, and Swing doesn't handle having multiple threads changing the same stuff very well. Now this topic here is more about performance, multi-threading for performance reasons, but it's good to know about anyway. And there's a couple of different choices in terms of higher level threading constructs. So these are constructs where you aren't actually creating the threads yourself and running them, but using other code to determine how many threads to create and which ones get your code. One is the fork join pool, which was introduced in JDK 1.7 and improved in JDK 1.8, and introduced a fork and join model for recursive threading. So these are cases where you want to have, say, one thread that potentially launches other threads and things like that. And this is a very very elegant way of doing multi-threaded code for performance reasons when you want to multi-thread when you want to multi-thread, say, a large data processing task. The idea with the fork join pool is that the process is forked, that is divided up into threads for lightweight asynchronous multi-threading. Those threads can in turn fork to create more threads. And when the threads all terminate, the results that they return are then all merged together until they're eventually returned to your application. So this is sort of a very elegant way of handling distributing data between threads and collecting the results at the end. Fork join pool makes use of something called a thread pool, which is where you go and create a bunch of threads in advance and pretty much allocate them to tasks as you need them. This reduces the overhead that you get when you're creating a bunch of additional threads. You don't want to be creating threads all of the time in a performance important application if you've got a lot of threads. Using a thread pool and reusing existing threads is, but just giving them more tasks to do, is the better choice there. This is some very simple code using fork join pool. So what I'm doing here is I have this array of integers, and I just want to calculate their sum. And so specifically I want to calculate their sum in the background while I do other stuff in the foreground. So I write my code into this compute method here, which is overridden. It's part of this recursive task specification here. And all this compute method does is it just calculates a sum. Then what I do here is I call fork on that, and then when I call join, I can just get the result back, and I can see what value I got from this operation, even after doing a bunch of stuff in the foreground. This is just a very simple example because this thread can then go and spawn other threads by using fork, and it's a very elegant way of sort of splitting up tasks and then combining together the results at the end. Note that I don't actually need to use the text fork join pool in this at all. I just need to create the task and then call fork and join on it, and it automatically gets used. The other operation is Java util stream, and this was introduced in JDK 1.8, and it's designed to let you very easily apply a bunch of operations to objects. Let's say you've got a bunch of things in an array list. You can then go and do something on all of those items very easily using this, and it also lets you perform those operations in parallel. So there's helper methods in Java util collection, so you remember all of the collection classes inherit from this, and those helper methods are stream and parallel stream, and we can use these in order to parallelize operations on, say, every element of an array list or a queue or something like that. And there's also some convenience methods available in arrays that make use of the same thing. So arrays, for example, has a parallel sort method that can be used for efficiently sorting a very large array if you have lots of CPU cores. And this is just a simple example of using parallel stream. So I've written this method here called capitalize that receives an array of string buffers. Note that I use string buffer, not string, and that's because you can actually modify the contents of a string buffer, whereas strings are immutable. So I've got this array list of string buffers, and then I call strings dot. So strings inherits the method from collection, parallel stream, and then I just call for each on that. And I need to pass for each a consumer. You can also use lambda here, but I've just used a consumer. So I've created a consumer and overridden the accept method, and all I've done here is just looped over the contents of the string and set every character to uppercase. So I've only processed one string here, but this method will be called on every member of this array list, and that will happen in parallel. So it will divide up this array list among my CPU cores, create a thread for each one, or use an existing thread because it uses it from a thread pool, just like fork join pool does, and it will then parallelize all the strings in that in one go. It will parallelize all. It will capitalize all the strings there in parallel, so that I can make full use of my CPU cores. So that's also a very powerful convenience method, and this is one that I've actually used in quite a few places for parallelizing Java code because I need it to run faster. Okay, so in summary, we've looked at threads. They let you run stuff at the same time. And we've looked at how you get threads to communicate, how you get them to synchronize so that they don't tread over each other's toes, and how you get them to notify each other when some particular condition changes. The notify and wait thing are sometimes seen in other threading libraries and other languages, and they're called condition variables. So if you see condition variables, you'll just remember that those are the same as wait and notify in Java. So homework, check out some of those demos. They're pretty good. And we'll be doing a bunch of stuff in the practicals for threads next week. And they're just about some basic thread work, setting priorities, and using dining philosophers, and exploring the dining philosopher's problem. So the take home for today's lecture: threads let us do more stuff or do stuff faster, but they can also be very dangerous. And thank you very much. Okay. You might have seen that there have been some small changes to the assignment, the way that it's marked in that announcement that was sent out. They don't really, neither of those changes should add to the amount of work you need to do for the assignment, but they are things you should probably still know about, especially if you're having issues with using MariaDB. So just check that announcement out if you haven't already, and I will see you next week. Thank you very much.